Welcome to the new unit. We are starting a new unit today, and it's going to really only get covered in around, I'm hoping, 2 lectures. What we're covering today is rate of change. Now, I assume you don't know much about calculus, but just to give you a heads up, this is literally all that calculus is about. Calculus is the intense study of how functions change. Now, while that might not sound all that interesting, the examples and ideas that we're going to come across today are going to show you that there's actually a lot that we can ask when it comes to how a function changes, how a thing moves through time, for example. So we're going to get an inkling of that today, and a lot of the ideas that we're going to have here are going to give fuel for word problems. So you may have noticed that in the past unit, we didn't do a lot of word problems. A lot of them were just, there's one right answer, you just plug it in, or do the work required. Sometimes there's some problem solving. Now we're heading into a unit where I can ask a lot more sophisticated questions and layer it with lots of words and paragraphs. Okay? So the first question we are going to ask is, what is a rate of change? And this is a question that is going to pervade the rest of this lecture, because it turns out that there's not just one answer. A rate of change depends on what kind of thing you're trying to study, what type of information you're trying to elucidate. For example, let's say you're going down the highway and you are going at 100 kilometers per hour and you want to be able to pass another car. To do that, you need to speed up. You need to change your velocity to a higher one, let's say 120 kilometers per hour, in order to be able to pass the car. However, you don't suddenly go from doing 100 to 120. Because you have to put your foot on the gas, you eventually get faster and faster and faster, and that's acceleration, right? So in that sense, that is a form of rate of change. You can think about how fast you're accelerating, how fast your velocity is changing. Okay, so that's one example of how a rate of change could get measured. But another example of a rate of change is a sort of like distance from a certain base point. So what I'm talking about is, let's say you're starting here, right? And then you're taking a walk to some place, right? And what you do is, halfway down the road, you realize you dropped something like a bag, and you decide to make a detour, right? Now you're here. You're here, right? The distance that you covered was technically this plus that little bit back, but compared to your initial position, you've only actually made it up to here, right? So maybe you could consider rate of change to be in terms of this base point, whereas if you had gone this whole distance, your rate of change was faster, the rate at which you changed your position was faster, but now that you're here, on average, it looks like the rate at which you change your position was slower, okay? If that's a little confusing, don't worry, we're going to go through a lot of examples, but I just wanted to give you the basic idea. Now we're going to see why we care about these rates of change. So I'm going to give you one example from every scientific field out there. That means biology, physics, and chemistry. Everything else is just a derivative of those. So in chemistry, oh my goodness. So in chemistry, where does a rate of change come in? Well, it usually comes in reactions. So you probably have not done grade 12 chemistry yet, but in case you know anything about reactions, you know that there's a certain amount of interest in the rate at which reactions happen. We are interested whether reactions happen very slowly or very quickly, and that will often depend on the chemicals involved and sort of the external environment. So for example, let's say I have a reaction that goes like this, where this top bar here is 100% completion, and over here is 0% completion, and this is the time axis. Okay? So what we see here is that this reaction is just going slowly, steadily to 100%. Okay? Whereas if I had another reaction that did sort of this thing, okay? Well, we could say a lot of things about how this reaction is different from this one. For instance, this reaction, the line looks fairly linear, so we can say that the rate of change of the reaction was fairly constant. Whereas this one, it seemed to sort of start off slowly and then speed up all of a sudden, but as it neared 100%, it got slower and slower. Okay? So all these are very intuitive ideas, but with calculus, we are able to make those precise and apply them formally to these fields. Another one is biology. Suppose you're doing a population growth experiment, and your population does something like a logistic curve. This is what we're hoping happens to the virus, right? So, as you can see, a rate of change is very important to know in this case, because we don't know, while we're in this pandemic, we don't know whether we are here on the curve, or we're here on the curve, or we're here on the curve, right? The number of cases each day is increasing, but we don't know for sure how fast they're increasing unless we take a general look at the data, right? So generally the way these pandemics work is that at the beginning, the rate of change of people infected, so this is people infected, and this is time, is that there's very few people infected, and then gradually more and more people get infected, and all of a sudden there's a spike. But then as cures come out, as treatment options become available, the rate at which people get infected decreases and eventually flattens out to nothing, right? And hopefully it'll just, go back down there. But that's generally the idea, okay? So as you can see, knowing how rates of change work is important to know in this context. Lastly, and this is the example that we're going to use for most of our discussion because it's probably the most intuitive one, is just regular walking and moving, right? So here's the situation. You are walking to a place far away. Here's the place, right? Now this is like distance from home. Now let's say the place that you wanted to go to was 1 kilometer away. Okay. Now, suppose you move something like this. Okay. Your path could be modeled by a function, right? So here you can see that you sort of walk steadily for the first little while, and then over here you start to slow down, and you realize you maybe forgot something again, and you turn back, stop again, and then you sort of go a little bit faster. You see the slope here is a little steeper, so you go a little bit faster to your destination, and this is time, by the way, right? So this is not literally the path you take, but it shows you how your distance from home changes over time. So here you got farther, here you got closer, here you got farther again, okay? In fact, most universities will require you to take a basic introductory calculus course in order to be able to do some sort of reasoning with respect to rates of change and their applications to the field. Okay, so let's examine that last example a little more carefully. So in case it wasn't super clear what was going on, you're at your house and you want to get bubble tea, which is over here. Okay, and the bubble tea shop is 1 kilometer away. So this is 1 kilometer away. So you go and take your walk, and you, like the first time you're going, it's pretty straightforward. You just walk there, and it takes you 1 hour. 1 hour to get there, right? What would your rate of change be? I think anyone could answer this. It's just 1 kilometer per hour because you traveled 1 kilometer in 1 hour. Okay? Now, how about this? You got your bubble tea, but now you need to go back. So let's pretend you go back, and it takes, double the amount of time. So now this whole trip, there and back, took you 2 hours. What then is your rate of change? Now this is the interesting question. See, if you're thinking about the distance that you walked, you would say, aha, well, I walked here 1 kilometer, and I walked here 2 kilometers, right? So the distance I traveled was 2 kilometers, right? And the time that you took was 2 hours. So that means your rate, speed is distance over time. So you should have done a rate of 2 kilometers in 2 hours. Oh, it's just the same thing as 1 kilometer per hour. Okay? And that's a fair answer, right? There's nothing wrong with this. But now suppose your mom was out in the back gardening, okay, and didn't know you left for 2 hours because they were gardening for 2 hours at a time. So you went, you came back 2 hours later, and now you ask your mom, how fast did I move? And your mom didn't know that you went there and back. All she knows is that you were here 2 hours ago, and you're here now. So as far as she's concerned, you didn't move at all. You didn't move at all in the 2 hours. Your displacement was nothing. And the time that we're looking at is, again, 2 hours. So to your mom, it looks like you actually traveled at 0 kilometers per hour because you just ended up back in the same place where you started. And that's also perfectly reasonable, right? So you can see there's a dichotomy here. That means that there's two different sides to the story, okay? There's one here that takes into account all the distance that you walked, and there's one that takes into account only the beginning and the end. And both are valid methods of measuring it, and we will be investigating both of these quite thoroughly, okay? But over time, our attention will be more focused on this, because we're going to eventually calculate something called instantaneous rate of change, which sort of starts to fail when you talk about displacement. Okay. All right, so now what I want to do is I want to graph this just to make it super clear what happened. So let's graph it and see what connections we can make between this situation and the graph. So in case 1, you just went to the bubble tea store, okay? The bubble tea store is 1 kilometer away, and again, this is like your distance from home. Distance from home, okay? So you just sort of like did that, let's say, okay? And you stopped here. This is time, and this is 1 hour, okay? My brown marker is dying, and I'm going to change it next lecture, promise. All right, so you moved 1 kilometer in 1 hour, right? So what was your rate of change? Well, as we saw before, you could just look at the beginning, the end, and your final time here was 1 hour. So you could say that you traveled 1 kilometer in 1 hour. Now, I didn't tell you how you got from here to here. All I told you was that it was 1 kilometer and that took 1 hour. But what would happen if I did this? What happens if you ran for a while and then took a break and then realized you forgot to get something, so you go back home, and now the bubble tea store is almost about to close, so you run back even faster than when you started, okay? Now that paints an entirely different picture. Yes, it took you 1 hour technically to get from here to there, but that's just looking at this point here and this point here. There's a whole story that went on here, right? And you personally will say, no. I did a lot in 1 kilometer. Let's say this is half a kilometer. Let's say this is 0.5 kilometers. Then what amount of distance did you actually travel? Well, you traveled half a kilometer, then half a kilometer back, and then a whole kilometer again. You actually traveled 2 kilometers, right? So what you think that you traveled 2 kilometers. Really, if you look there and there, you only traveled 1 kilometer. Okay? Now, this is the notion of distance. Okay? Distance is the amount of like terrain that you literally cover. But this here is displacement. It only takes into account the beginning and the end. You want to know what your displacement is? Just look at how far you were from the start, from the end, and subtract it by the start. Okay? That is your displacement. Okay? So this we call displacement, and this we call distance. Okay? Get those two terms separate in your head. It's very common to mess these two up. Okay? Now, associated to each of these, we can have a concept of average speed and average velocity. Okay? So, velocity will always belong to displacement. Okay? Velocity. and speed will always belong to distance. Okay? Now you may be wondering, if you haven't taken physics, what's the difference between the two? Here's the difference. Speed is just concerning distance, right? Ignores direction though. Right? Velocity, here's the thing about velocity, it has an associated direction. Let's say the bubble tea store is north of your house. Let's say this is north. Right? So your velocity would be initial minus final, and then you had action. It was north. You traveled 1 kilometer per hour north. Okay? So over this whole time, you traveled 1 kilometer per hour north. So our velocity here is 1 kilometer per hour north. Okay. If you take in physics, this should be pretty easy. Now speed, remember, it ignores direction. All it's concerned with is how far you actually walked. And we just saw that you walked 2 kilometers. So what we're going to do is to calculate average speed, right? To calculate your average speed, all we're going to do is we're going to take that distance that you traveled, which was 2 kilometers, and divide it by that hour that you walked or ran. So it's 2 kilometers per hour. Notice that there's no associated direction on that. Okay? So hopefully that example was clear. Right, so now enough with the examples. We're going to go like completely abstract. Okay. So consider a completely abstract distance time graph. Okay, with an associated direction, which just means that we are able to calculate velocity. Right. So this is a distance, but like it's a distance traveled in some direction, so we'll say, we'll just keep it north for now. I'll put bracket n for north. And this is time. Okay? So consider some random path that you could take, like maybe like this. Okay? This is a perfectly valid path. You just started a little bit farther away from 0. Okay? So you're allowed to start anywhere. Okay? So now, what are the two concepts I want to get out of here? I want average speed and average velocity. Okay? Right, now to calculate these, we need the following. For average speed, we need distance. And for average velocity, we need displacement. Okay? And we're going to divide both of these by time. This is an important formula. It's not complete, but it's an important formula to know anyways. You should already know this from previous math courses, but in case you've forgotten, I'm just making it explicit here. We're going to tweak these a little bit to make it work with our function stuff. Okay? So here's how we're going to do that. To find distance is a little more difficult because you have to take into account, going back and forth, back and forth. So let's just do displacement first. Displacement is easy. Displacement is defined as as final position minus your initial position. Okay? Here, if you're at 30 meters, and at the end here, you ended up at 100 meters, your displacement was 100 minus 30. That's simple. Okay? 100 minus 30. So you displaced, over that period of time, 70 meters. Okay? So that's average velocity. On the other hand, now we're going to consider average speed. So what is average speed? It's distance over time. So now we need to find a way to calculate distance. Okay, well, here's the problem. You can't exactly read it off the graph, like just knowing your function. You have to sort of see, like, where you went down and where you went up and where you went down and where you went up. Because every time when you did these like turns, you have to take that into account. All that is distance that you traveled, right? So the formula for distance is a lot more difficult, and I can't like write it down as neatly as the displacement formula. all I can do is tell you that you need to take into account first this distance that you went down, and then you need to take into this distance when you went up, and then you need to take into account this distance when you went down, and then that distance when you went up, right? So hopefully you see that you went down first, and then up, and then down, and then up. So adding all those together, all of these distances together, you'll be able to get your final distance. Now, we're gonna move away from average speed and more towards average velocity. We're more interested in direction, and this is a much nicer formula to work with because it plays into something that we know very well, which is the slope of a line. Okay, so I just want you to be able to understand what average speed is. Okay, and this should be the level of understanding that you should have. So if I gave you a graph, you should be able to calculate for me the distance over time to get your average speed. All right. So the moral of all this is the following. I'll write it big in red and then erase it right after because I have no space on the board. Speed and velocity. The difference between the two is speed cares about where, sorry, it's the other way around. Velocity cares about where you ended up. And speed cares about what it took to get there. You can make some sort of philosophical life story for yourself in order to remember them, but all that matters is that you remember them. Okay? These are terms that you must memorize. These are definitions that you must memorize. Now, let's delve into average velocity a little deeper. We're going to explore something that's going to lead to like an actual calculus concept. You may be wondering whether I'm going too off the rails here with the calculus stuff. I'm not. This is literally what is taught in advanced functions. So to me, it's a little ridiculous that they don't just call the entire thing calculus, because half of what you do in advanced functions is literally calculus. Although a little unrefined, if I might add. All right. So let's draw that graph again. Okay. And let's make it simpler this time. Let's just do that. Okay. So again, average velocity would be your displacement over time. Now what your displacement is your final position minus your initial position. If we think about this brown curve as a function, let's call it now f of x. It is a function because it, okay, you know what? This brown marker is done. It is a function because it satisfies the vertical line test, of course. So what we can do is we can evaluate our function here and here. That's what we're interested in, right? So what data can we get about these 2 points? Well, of course, every point has 2 coordinates. These are assigned to time values. For now, I'm assuming we're starting at time equals 0. So let's put a 0 here, and let's put like a number. We're not going to put a unit on it anymore. We're just going to put like 3 or something. Okay? So I put a 3 here. Let's just give these random numbers like 1 and 5, for example. Okay? Then we would calculate our average velocity as 5 minus 1 over 3 minus 0, which is equal to 4 over 3. Okay? Thus our average velocity, displacement over time, was 4 over 3. No units, because right now we're dealing purely with math, no physics. Okay? Alright, so now, what can I do with this? I can remove all the numbers and just give you a general idea of what happened. Okay. So, let's see. Let's say, actually, I wanted to change this. And I wanted to track my average velocity starting from here for some reason. Okay? Maybe I turned on my information gathering sensor, and then I only wanted to start collecting data here, but it collected some data before, so whatever. Okay. Again, I have the same deal, 2 points. Okay. We are going to call this one T0 for time 0, t1 for time 1. And this, of course, is going to be f of t1. And this is, of course, f of t0. So we have these 2 points, okay. Now to calculate our average velocity, all we have to do is do displacement. So a little more notationally heavy, but still we're doing the exact same thing. And subtract by the difference in time. So that's t1 minus t0. Now this should be jumping out at you. This should be like, hold on a second, haven't I seen this before? And in case you don't see immediately what exactly this means, well, let me try and make it more obvious by drawing this line here. Okay? Now, think about it for yourself for a minute. How does this expression relate to this line? How does it relate to this line? Okay? And the answer is that this expression gives you the slope of this line. Let's call this line L. It's a line, y equals mx plus b. Okay? And the slope m is in fact this expression. How do I know that? Because it is the rise over the run. Okay? This should feel very nice now because we somehow managed to tie in this completely abstract concept of velocity to our grade 9 curriculum. It's just the slope of a line. Okay? But maybe that was a little bit obvious. Okay? Alright. But hopefully that makes sense because that is literally all I wanted to say about average velocity. So average velocity can be understood as the slope from your 2 endpoints. Okay? If this is your beginning point and your end point, all you have to do is take the slope by doing this. Let me box it up so you remember. And then that is your average velocity. Not too difficult. Now, I'm going to consider a much more difficult question. And that question is, how fast was I moving throughout this duration, throughout this time interval? In particular, let's say I wanted to know how fast I was running. Let's say I'm running here. Let's say I want to know how fast I was running at t0. Now that might seem like a very strange question to ask. How are you supposed to be able to get that from the graph? All you have is like just a bunch of points, right? But clearly, and you already have this from your intuition, you just look at the slope here and the slope here, right? Clearly you were running faster here and slower here. How much faster? How much slower? We want to quantify this information in math. So let me show you how you might be able to quantify it. Okay? And my idea is this. Just given some function, to figure out how fast I was moving, all I have to do at a point, let's say I want to figure out how fast I was moving at this point t0, all I have to do is look at the slope there. But there's no slope. I mean, like, to get a line you need 2 points, I only see 1 point. Well, that's exactly the idea. I'm going to draw something called a tangent line. Okay, this is called a tangent line. Perhaps you've heard of this term before, used to describe tangents to a circle or tangents to a plane, things like that. But here we're going to use it in relation with a function. So all this means is a line that intersects the function locally once, i.e. at a point. So what that means is that this here just barely like grazes off the surface of the function. It just touches it once and then it's gone forever. Okay? In some jurisdictions, they call a tangent line osculating curve. And this is a term that I found helpful when I was learning this for the first time. Osculating in the Latin derivative means to kiss. So you can think of this line as kissing the purple, the red line as kissing the purple. It just hits it once and then it departs. Okay? So in other words, it does not do this. Maybe some non-examples are actually more helpful than examples of tangent lines. So I'm going to draw that same curve roughly. So here's a non-tangent line. Okay? It does not kiss the purple curve at that point. It sort of like runs right through it. We want it to like just graze the surface, okay? Yeah, I think that's a clear enough non-example. Okay, so where do I want to go from here? Well, I want to be able to quantify this, remember? So the way I'm going to quantify this is look at this tangent line and then pick out its slope, right? Because it's a line, so I can get its equation, probably, y equals mx plus b. I mean, let's just think about how we would do this. I mean, to solve y equals mx plus b, we need, of course, m, we need b, and then we're done, right? The only tool that we have right now is this point, so we can substitute something to y equals y and x. But beyond that, we don't have a lot of information. But if we did have the slope of this, if we had the slope of this line, that would be really helpful, right? And the slope of that line is actually a pretty good indicator of how fast you're moving at that moment, right? So the idea is, if you're moving really fast like this, right? If you're moving here really fast, then the slope is steeper. If you're here and you're moving slower, the slope is closer to 0. Okay? This is exactly what we are going to be measuring. So the study of calculus, at least the initial part of it, is literally just figuring out how to get these tangent lines, figuring out what the slope of this tangent line is. Okay? So let me write down that expression as our goal. So our goal now, figure out how to get the slope of a tangent line to a graph. And remember, we are interested in this because if we were able to do this for every function, then what we could get is we could get a measure. So this would yield a measure for how fast the function is changing. And as I explained before, there are a lot of different scenarios where this information is very important to know. All right. So, just looking at the time, we have enough time to go through the basic idea of how we're going to tackle this problem. And it's not a simple problem. This took mathematicians quite a long time. It, in fact, took them a couple hundred years to figure out that this was the right thing to deal with. And surprise, surprise, it has to do again with limits. All right. So here's the idea for how we're going to do this. It's a very ingenious idea, but when you first look at it, it doesn't seem very effective. At least it's not very efficient. So let me just prepare my thing here. Okay, so again, my question is, what is the instantaneous rate of change at that point? Okay, so again, right, I should probably mention this slope we are going to call the instantaneous rate of change. Because really, that's what it is. I mean, there's no other way to put it. That's what instantaneous rate of change is. It's how fast you're moving at that moment. Okay? Alright, so here's my idea. Here's my idea. Remember how we had the idea of average velocity over time? Let's do that again. T1. Okay? We'll draw a line like that. And, you know, it's not a tangent line, but, you know, it's something. Okay? This is pretty bad as an approximation. If I were going to call this the tangent line, you would definitely say, no, that's definitely wrong. But then I would challenge you in return and say, well, can you come up with anything better? And maybe you might be smart about it and think, well, yeah, if this is the only tool I have to work with, then yeah, there is something better. And maybe what you could do is pick a point a little closer, like that. Right? Because I know 2 points. If I have 2 points, I can make a line. If I make a line, then I know its slope. Right? So maybe you would consider these 2 points on the function and do that. Aha! Look, I did it. Well, not really, right? Because if I zoomed into here, you would see that our image looks kind of like this. So, I mean, it's better. It's better than the first one, but it's clearly not close enough. So, okay, well, I'll do you one better. I'll move the line, the point here even closer. I can move it as close as I want, but as long as it's not the same point, I'll still have two distinct points. With two distinct points, I can make a line. When I have a line, I can figure out its slope, and that gives me an approximation to the instantaneous rate of change. In fact, that's exactly the idea. The idea is to move this point really, really, really close to the purple, and then hope that it gives you a nice answer. That sounds like a really bad idea, because what it means is that you would have to try for a couple of values. You know, you try for this value, and you say, oh, no, that's not close enough, so then you try this value, right? And that'll give you a new tangent slope. But you say, no, it's still, I can still do better, right? So you'll move it even closer, and then, you'll get something better. You keep repeating this, and eventually you might get somewhere, maybe. You'll never get it exactly on the point. You can't. You literally can't. With one point, you cannot create a line. But with 2 points, you can. And that's the foundation of this entire idea. So let me just write that down. So foundation is that 2 points yield a line. And not just any line. It gives you the entire equation of the line. A line y equals mx plus b, right? And as the points move closer together, the line becomes a better approximation to the tangent. Okay, I'll move out so you can copy that down. Okay, so this is really what we're interested in. All right, now let's make that precise. Let's make that very precise. So how is our idea going to work with what we already know? Well, we know how to calculate average velocity. That's the good thing, right? It was just, what was that formula again? I'm starting to forget myself. It's like f of t1 minus f of t0 all over t1 minus t, something like that, right? So that was, right, that was the slope of the line, right? But remember, what we're looking for is the slope. And if our line is going to get closer and closer to a tangent line, maybe this value is going to get closer and closer to the slope. The slope is what we wanted. So this is really what we need to be looking at, right? What we need to do is pick points t1 and f of t1. So this is going to be t1, f of t1, that are really close to t0, and those are going to give us good approximations to the tangent line. All right, so that's reassuring. But again, we want to do better. And we can see that every time I pick a point, if I fix a point and say, I want to choose that one, someone out there, some clever person, could always come up with a better point. You just, you can take halfway between t0 and t1, and there you go, it's a better point already. Okay? And so, this is not good enough, but what we are going to do here is one small little adjustment. Okay? So now the idea here is to move this point closer and closer and closer to this coordinate right here, which I'm going to call, just to confuse you a little more, I'm going to call it A. Right? Here's A, here's f of A, and this point that we're going to slide towards it, the one that was before t1, I'm going to call it x. Okay? So then this y coordinate is just going to be f of x. Okay? So now our goal, remember, is to move x as close to A as possible. So that suggests something. We should take the limit here as x approaches A. So as x gets closer and closer to A, this will give me the slope, right? So over here, it'll give me a slope. As x gets closer and closer to A, it'll give me another slope. As x gets even closer, it'll give me another slope, okay? So this is the actual thing that we are going to want to work with, okay? And just to quickly tie it into what this is projecting towards in calculus, this is the definition of a object in calculus that we call the derivative. Okay? And this we're going to be spending a lot of time on in the calculus unit. Okay. So make sure you get that formula down. Don't worry too much about being able to work on it right now. That is all stuff that we're going to throw into the next lecture. So next lecture is going to be literally just a bunch of examples, and we're going to do this a couple of times, and we're also going to use another method to evaluate these tangent lines. Okay. So let me just, let's see. One thing I do want to mention though is that notice right away that you can't use substitution. It's not going to work, because if you just put in a in here, like we did before, where we just put the number here in for x, you get 0 in the denominator. So that's not going to work. We're going to have to come up with more clever methods of evaluating these limits. It's not like the ones that I showed you in Unit 1. Okay? But I thought it was a good idea to bring in the idea of a limit so that this is not the very first time that you've seen the notation. I know it does look daunting right now, but as you get more practice with it, and next lecture you'll see it a lot, I'm hoping that this will sort of facilitate the process of going from your regular advanced functions math to calculus math. Okay. So next up, I'm going to actually do the same thing, but a different way. This is but one way of trying to answer this question that we had of finding the equation of a tangent line, or the slope of a tangent line. So let me just recreate my image here. I'm going to label a couple of things differently. And I'm very sorry about this, but the standard way that this is taught is not very helpful. It's not very helpful at all, because it sort of tries to confuse you with the two methods. So let me just draw our picture again here. And you should draw the picture again too, because even though it looks the same, the labeling is going to be different, and if you don't keep track of the labeling, you're going to have a lot of difficulty. Okay. All right, so let's say the point that I wanted to evaluate is this one, right? Now, instead of calling it A, I'm going to call it X. I know it's horrible, because that's X is what we used for the sliding thing last time, but now I'm going to call this fixed one X. Okay? I'm very sorry about that. There's nothing I can do. It's not me who came up with the terminology. So, of course, this point's coordinate is x, f of x. And now we're going to play the same game. Except we're going to do one thing slightly differently. So remember, the game that we play is we pick a point over here, and we take the tangent line, we take the line that connects both of these 2 points. Because we have 2 points, we can create the equation of a line and therefore determine its slope just by looking at the equation. Okay? And then we're going to move this point closer and closer. Okay? So here's something that you may want to think about. Last time we called this something else, right? But what if I think of it not as another point? What if I think about it in relation to x? In other words, this point here is just x, but you have to add like a little something to it. Let's call it h, right? So let me just put up here, h is a little number. Okay? So I add like just a little bit to h, and I'll get a point here, and then this point up here is just going to be f of x plus h, right? It's going to be x plus h, f of x plus h. All right? So hopefully that's not too confusing. Now what I'm going to do is I'm going to, again, move this point closer and closer and closer to x. But what's happening there is that I'm changing this as well. And how am I changing this? I'm just making h smaller. I'm literally making h smaller. And ideally, I would like h to be 0 so that I could get the instantaneous rate of change at x. However, I know I can't do that because 1 point you can't make a line. So what I'm going to do instead is I'm going to make h as small as possible, as close as possible to 0, and then figure out what the resulting line is. And our hope is, if we make h small enough, we'll get a good approximation to the tangent line. So let's do that. Again, the slope of our line, right? We're going to use the exact same formula as before, except this time our t1 is x plus h, our t0 is just x, and we can just replace everything in, right? So we have f of x plus h minus f of x all over x plus h minus x. Luckily for us, x and minus x cancel out, and we're just left with this. Okay. Now remember what I said. I wanted to make h really small. I wanted to make it go to 0. right? Ideally, I want h to be 0, but I know that's not possible because if h was 0, then I'd only have 1 point. I need 2 points. I need 2 distinct points. But what I can do is I can make h really small. So what I'll do is I'll do a limit, and maybe you can guess now, actually try and guess. We're trying to send h to 0, okay? Again, notice that you can't solve this limit using the same method we had before, using continuity, because this here is not continuous. We have in the bottom h. If h was 0, then this expression would not be would not have a value. It's a non real number value. Okay, so this is your second formula for evaluating. Okay, let me write the other one again. So the other one is limit as x approaches a of f of x minus f of a, all that over x minus a. Okay. Now I will list the similarities and differences. Okay. So here what we have is we have a limit, right? And what we notice is that x, f of x, is fixed. That means it doesn't move while I'm trying to evaluate the limit. But h is a small value, right? And it moves closer to 0. And what moving h closer to 0 does is that it makes x plus h gets closer. Sorry, it moves x plus h closer to x. Right? And that's how we're going to evaluate the slope this way. Now on the other hand, here we also have a limit, and maybe I should mention on here as a similarity, not solvable by continuity. Okay, that's my shorthand for continuity. So this one is the same thing. It's a limit, and it's not solvable by continuity. You can't plug in a for x. So not solvable by continuity, okay? But now instead of x and f of x being fixed, we have a, f of a being fixed. Very confusing. I'm very sorry about this, but this is the standard notation, and I'm not here to reverse hundreds of years of standard notation. I'm just here to teach you the basics and carry you through the advanced functions curriculum. Now, a is not just a small value, it is a value very close to x. X is the sliding value, right? X is very close to a, right? And what we want is we want x to move closer and closer and closer to a. So a gets close, x, see this is confusing me now, x gets closer to a, right? All right, so yeah, I know it's a mess, and I've done very few examples with this, but not to worry because all the examples are going to come in next lecture. The next lecture is going to be pretty much filled with examples. I'll do so many of them, you'll get sick, and you will have seen everything under the sun that could possibly come up as a type of question that evaluates these things. But this is sort of where we're going to stop our venture into calculus. And next lecture, what we're going to be doing is we're going to be answering the questions that we wanted to answer using real examples. I'm going to involve some straight up applications to just some regular functions, but then I'm going to mask it up later with some word problems and show you how to tackle those as well, because they can get quite intricate, and if you're not prepared to solve them and dig through them with this, armed with this new tool and this new notation, you're going to have a lot of difficulty. Okay, so although this unit is only going to take a day to get through theoretically, the ramifications and the formulae that come out of it are here to stay for a very long time. And by very long time, I mean until the end of the course. Right? So that's all I wanted to do for today. If you have any questions on this, because I know this is a very confusing concept, please, please, please ask questions about this. There's a lot that I can do to try and make this more easily explainable, but at the end of the day, the onus is on you to understand why this is true. I mean, why we have this in here, why we have this in here, what each of these two methods is doing, and why the limits are the way they are. Why does h go to 0? Why does x go to a? The final note that I want to make is just, in the future, I'm just going to be referring to them by their names. Okay, so this one is called the h method because it has h in it. But some people I've seen also call it the step method. Okay, so I will usually refer to it as the h method. You may hear it referred to as the step method. This one is called the x minus a method. Okay, everyone I know calls it that. Everywhere I've read calls it that. It's the x minus a method. Okay, so I mean, the obvious thing that pops out at you is that the name is just based on the denominator, and yeah, that's it. Okay. All right, so that's all I wanted to do for today.